All right, average value and the mean value theorem. Now, you're not imagining things. There was a mean value theorem back in derivatives also. Had to do with Rawls' theorem was a special case. Now that had to do with the slope. If you have a curve between a couple of points, like if a curve goes like, whoa, then if we take the slope, sort of the average slope of this curve would just be the slope from point A to point B. Oops, not a very straight line. But the point is if we're going from point A to point B, and you found the slope of this line, the mean value theorem of derivatives just said that, hey, you know what? If this curve is continuous, then at some point along the curve, the slope of the curve at that point of the derivative will have the same slope as this. So obviously on this curve, it would be kind of like right there and down here. There's a couple of spots where the curve is for a moment parallel to that average or mean line between point A and point B. So pretty boring theorem. The thing after that was Rawls' theorem, which is a special case where A equals B, and therefore the derivative would be equal to 0, and that's what sort of led us in to maxes and minima. What's happening with this one is we're going to find the actual average value of a function. So in this case, instead of worrying about slopes and stuff, we're going to be finding the average value of the function. So the function's going from here to here, and I'll show you in a second. This is the formula we're just going to use. So basically, it's really a pretty simple chapter, just because if anybody ever asks you the average value of a function, bam, this is the formula. No worries, and I'll show you how to use it in a second, and then we'll do some word problems in the next video, because that's often how they do it. But it's really straightforward, just because if they ask you the average value, there's pretty much nothing they could ask you other than, hey, find the average value. There's one thing they could ask you, and we'll get to that in a second, but yeah. So what does the average value mean? Now, this is just a squiggle on a graph. Obviously, it's probably not a polynomial because it's got some weird kinks in it and stuff. But the point is, there's just some graph, it's some function, whatever it is. Let's think of this as a real world example you might want to know the average of. So for example, if you've ever seen the stock market and like a graph of a stock, you know how it kind of goes up and down and stuff, you might want to know the average price of that stock over the course of a day or the course of a year or something. Something that takes all the rises and falls out of something that's kind of bouncy, or the average wind speed during a hurricane. Gusts come, then lulls, so the wind's all over the map. Maybe this is a graph of the wind during a hurricane. So you might want to know the average wind speed. Or, this could be the speedometer in your car. So you drove for 6 hours on a road trip, and this is your average speed. You saw a cop for a while. You went through a town, had to slow down. Then you took off. Then you saw a cop and slowed down really quick or something. And but what's your average speed over the course of that drive? You could just take your total distance. Wouldn't you just take your total distance that you covered and divide it by the number of hours you were driving to get your average miles per hour or kilometers per hour? Yeah. So what we're trying to do is we're trying to find that average speed that if between the hare and the tortoise, if your actual speed was doing all this crazy stuff, the average speed would be the speed at which you could have gone steadily the whole time and covered the same amount of distance. Well, it turns out the way you find average speed is essentially what you're doing is you're saying, you know what? If this is the integral, if this is a chart of velocity, like how fast I was driving the whole day, so this vertical axis would kind of be velocity. So the speed you're driving, turns out the distance you cover is the integral of velocity. So basically it's just the area under the curve. If this is my speedometer readout during the course of this drive, this area under the curve would be the distance I cover, because distance is the integral of velocity. So what I'm looking for, the average value, the average speed I was going, is going to have the same area. I just want to find a horizontal line that when I shade in under that, I get the exact same amount of area in that rectangle as I would have had if I integrated all the area under this crazy shape. So the two areas should be equal. And that's where we get this equation. So the average speed is going to be the integral from A to B. And A to B are just, that's the usual interval deal. So your starting point, your end point, that'll be A and B. It's just x coordinates of this chunk of area. And you're just going to integrate the function. So in this case, we'd be integrating velocity, but it's just the integral of the function from A to B. That gives us the area, right? But then how do I find the average value? Well, let's see. This rectangle is going to be, the area of the rectangle is going to be the width, or the base of that rectangle is b minus a. And then the height is the average value, right? just that y, the height of this is just the average I'm looking for. That would be the y coordinate of that horizontal line that would represent the average. So if I want to solve this for average, don't I just divide by b minus a? So if I divide both sides by b minus a, I've now got what my average value should be. And that's all we've done over here. The area of the rectangle is the same as the area of this, so that's just all this stuff. And I need to divide by b minus a in order to solve for the average. And of course, that's not what the formula I showed you a second ago. That formula was like this. They just put the 1 over b minus a out front. But the point is, we're just going to take, this represents the area of the rectangle we're looking for. This is the height of that rectangle, so we got to divide by the width of the rectangle in order to get the average. So that's where that formula comes from. That's what we're trying to look for. But then once you're actually doing the problems, it's really straightforward. The average value is just 1 over b minus a, integral whatever. So let's take a look. I want to find the average value of y equals 5 minus x. You don't even have to know what this function looks like, but it appears to be a line, 1, 2, 3, 4, 5, with an intercept of 5 and then a -1 slope. So it's going down like this. 1, 2, 3, 4, 5. Probably hits that point actually, but point is it's a line going down to the right from a y-intercept of 5. But we don't even need to know that because all we're going to do is a simple integral. So it's going to be 1 over b minus a, so that's 4 minus 0, times the integral from 0 to 4 of f of x, which is just 5 minus x, dx. Plug and chug. So we got 1/4 times the integral of 5 minus x dx. So that's 1/4 times, 0 to 4. So that is 1/4 times 5x minus x squared over 2, evaluated from 0 to 4, which equals 1/4 times, so if I plug in 4, I have 20 minus 16 halves, which is 8. And now I'm going to plug in 0, but that's just going to be 2 zeros. Alright, so that equals 1/4 times 12, which equals 3. So hopefully you saw that was just plug and chug. This is the formula. I would recommend just memorizing the formula, and that'll be good enough. Alright, find the average value of this thing. Alright, well it's just a different formula, different function, but the same process. They gave us an interval, so from 0 to 3. This time I gave us the graph, but that's just to show you, roughly what's going on. The average value is going to be somewhere between here and here. It's going to be along this, I don't know, maybe it's like right there. Kind of looks like decently accurate, but who knows. So what I need to do is just plug in and plug and chug. So I get 1 over b minus a, so that's 1 over 3, times the integral from 0 to 3 of x squared plus 1 dx. The reason I put the parentheses around here is just to make it really obvious that I'm integrating x squared and 1. But so you get 1/3 x cubed over 3 plus x evaluated from 0 to 3. Alright, so that's 1/3. So first I need to plug in the top limit, which will be 3 cubed over 3 plus 3. Then I got to subtract plugging in the bottom limit, which is 0. That's just going to be a bunch more zeros. Alright, so that's 1/3. 3 cubed is 27 divided by 3, just 9, plus 3, so that's 1/3 times 12 again, but this time it's 1/3, so it equals 4. Alright, so finding the average value is that easy. There's just one other type of problem they could ask you, and that is to find out what is the point, the magical point C, where the average value is happening. So this is actually exactly what happened when I showed you on the first slide of this deck, this video. That first thing I showed you, going back to the mean value theorem in derivatives. Not only did they ask you, hey, what's the slope between A and B, but what they asked for was, hey, tell me the point. So if we had a curve like this, and on the mean value theorem with derivatives, first you always calculated the slope between here and here. But then they asked you, hey, there's a, if this is A, x equals a and x equals b right here. They ask, what's the point C? Mean value theorem said that this point exists where the slope is parallel to the line. But then they ask for what is that C coordinate? What's the x coordinate that has a slope equal to that? And they're going to kind of ask the same question on these mean value theorem things with integrals. So we already said that, hey, the mean value or the average value is just, you want to find a rectangle basically with the same area as all this would have had. But then, so that's what we've been finding is the y coordinate of this rectangle, the average value of y over the course of this curve. That's what we've been calculating in the last couple of problems. But now they're going to ask, hey, at what values of x does the original curve basically cross this line? So they're looking for this point, they're looking for this point, they're looking for this point, they're looking for this point. And obviously this is a made-up function, so it has a lot of these crossings. In a normal function, you'd have like maybe one, you'd have one, maybe two. The mean value theorem, though, says that there has to be at least one if it's a continuous function. And of course, the two we just looked at, like a parabola, a line, those are continuous functions. So at some point on the interval, the line's going to have to cross the average value. And that's the coordinate we're looking for. All right, so now we're going to give a shot at actually solving for that C value. Because this time we're asking for the average value and C. And it seems like the only way they can ask, or the way these problems tend to be worded, is they'll actually mention the mean value theorem. Because otherwise asking you for the point on the curve that equals the average value or something is like pretty awkward. So anyway, it's hard to make a very clear question that tells you exactly what to do without mentioning the letter C and the mean value theorem. All right, so let's get started. Plug and chug is just, so we need the limits of integration. 2 minus negative 2 is 4, so we got 1/4 width from negative 2 to 2 of 9 minus x squared dx. And I'm actually, just to make the math a little bit easier, I'm going to use a trick, which is, this is a symmetrical function. It's an even function because it starts at 9 and it kind of goes down like this. So the integral of this whole area between negative 2 and 2, which is not quite the whole parabola here, just sort of this area, the area of that is just going to be twice the area from 0 to 2. So I'm going to rewrite this as 2 times the integral. So let's put a 2 in here and switch this to 0 basically. So we end up with the integral of 1/2, 0 to 2 of 9 minus x squared. If you'd prefer to work it the other way and just, go from negative 2 to 2, go for it. But the fractions get a little bit ugly. All right, so we got 1/2. Integral of 9 minus x squared is just 9x minus x cubed over 3. And we need to evaluate that from 0 to 2. So that's 1/2 times 9 times 2 is 18. Minus 2 cubed is 8 over 3. So distribute that in, I got 9 minus 4/3, just multiplying in the 1/2. Now I did not forget to plug in 0, it's just that the great thing about having a 0 as a lower limit is when you plug it in, you just get a bunch of zeros. So that's the nice thing about having 0 as the bottom limit. So we got 9 minus 4/3, which is 27/3, minus 4/3 is 23/3. All right, so that's my average value. So that's the first thing they asked for, is the average value. But now we need to figure out that value C. So what we're going to do is, so now we've just figured out that the average value is 23/3, which is kind of up here somewhere. I don't know, maybe it's like right there. So the average value, that's just, if you're looking at all the y values along this part of the curve between negative 2 and 2, you can see that kind of makes sense that the average value would sort of be somewhere in the middle there. And then the mean value theorem tells us that at some point, because it's a continuous function, the curve itself is going to cross that average value, this horizontal line at the average. So we're just going to solve for this point and this point. The way we do that is we just set the original function equal to the average. So that means that 9 minus x squared needs to equal 23/3. Which seems like a pretty nasty problem, but let's take a look at it. We just got to get x squared by itself. So we'll get x squared equals 9 minus 23/3. Just rearrange that equation. which is 27 thirds, minus 23 thirds, which is 4 thirds. All right, so if x squared equals 4 thirds, I'm just going to square root both sides. So I'll get x equals plus or minus. Remember, whenever you're square root an equation to get x by itself, to get rid of x squared, you got to do plus or minus. So square root of 4 is 2, and root 3 downstairs, which is really plus. We got to rationalize this, so that's plus or minus 2 root 3 over 3. All right, so does it make sense we got a plus or minus? What's up with that? Well, yeah, in this particular case, because it's a parabola, it does in fact cross twice. So one of those crossings is a positive 2 root 3 over 3, and the other one's at negative 2 root 3 over 3. Cool. All right, this is the last one we'll do. Finally, because I love trig so much, hey, let's drop one in. What's the average value of sine on 0, 2 pi? All right, and we could also solve, of course, for those points C. So first we got the average. It's going to equal 1 over b minus a, so 1 over 2 pi times the integral from 0 to 2 pi of f of x, which is sine x dx. All right, so this one's a little more straightforward. 1 over 2 pi. Integral of sine is just negative cosine. And we evaluate from 0 to 2 pi. So that's going to be 1 over 2 pi times negative, let's see, cosine of 2 pi is 1. Now we subtract, and now I plug in 0. Cosine of 0 is also 1, but it has a negative sign in front of it. So that's actually negative 1 plus 1 is 0, so this whole thing just equals 0. That's kind of crazy. How is that possible? How could it have an average value of 0 on something that obviously has value? Well, check it out. If you integrate, if you look at the graph of sine, our original function is sine. So if you look at the graph of that, doesn't it go up and down? And it does so every 2 pi. So it starts at 0, and then at pi it crosses again, and then it crosses again right here. So the average value, we spend half our time above the axis, half below, so it just makes sense your average value would actually be 0. And you might be wondering, hey, but that doesn't make sense because we just integrated, so didn't we just find all this area? You know, this first part of the equation, we take the area under the curve and then we divide by 2 pi or whatever, but the point is that we find the area and then divide by 2 pi. So why is this area 0? Just looking at this, I see a lot of area there. And that is true. The problem is that area below the x-axis, and I talk about this in the definite integrals chapter a lot, but the area below the x-axis is negative area because that's just the way integrals work. So what it's doing is saying, you know what? This portion where we go above the x-axis, that has positive area, but then this lump below the x-axis, it's the same physical size, but because below the x-axis it's negative, so when you add those two areas together, you get an average value of 0, or you get an area of 0, and then of course when you take 0 and divide it by 2 pi, you get 0 again. So then the last part of the problem is find c, but the way we do that is we just set the original function equal to the average we found, which is 0. So x is going to equal 0, and it'll equal pi, and then if you really care, it might be 2 pi. Since it looks like we have a square bracket, which means we're including the 2 pi. You know, that interval notation, that square bracket means you're including 2 pi, so that means 2 pi is a valid answer. So we actually have 3 answers for C. Or, you know, maybe you just put down pi, because it doesn't really seem like it's crossing the value if it's at the end point, however you look at it. So that is the average value. It's pretty straightforward. They're kind of always the same. So cherish that. In the next video, we're going to take a look at word problems, which is going to be the exact same thing we've just been doing, except we'll put it in wordy situations that are kind of like the real world, like people driving, water flowing into things. So stick around for that.